Welcome back to Codex. Our speaker today is Ryan Matzke from Vanderbilt University. Ryan's research is in potential theory, discrepancy theory, and discrete geometry. Today, he'll tell us about minimizers of p-frame energies. Take it away, Ryan.
Yeah, thanks. Thanks for the introduction. And yeah, thanks to all the organizers for having me here. I was actually going to give a talk last semester, but got sick. And so this is a little bit of a different talk than I was going to do back then. It's a little bit, it has bits and pieces of a number of different papers that I've worked on. And the topic's one that I could probably talk for about 3 hours on very excitedly. So I'm trying to condense and focus on just a few things, but hopefully you all find it interesting. And it's been with a variety of collaborators too. So hang on, let me get that out of the way. There we go. So the objects that I work on primarily are what I'd call energies. So given some metric space, generally you can assume it to be compact, and some lower semi-continuous kernel, symmetric in two inputs. We call the discrete energy of some point configuration in whatever your space is as the sum of pairwise interactions between points. Easy way to think of it is just electrostatic potential energy for a bunch of electrons interacting with one another. Generally speaking, we're looking at kernels that just depend upon distance, and when distance is close to zero, are decreasing. That can be interpreted as particles repelling each other at short range. And then we start asking questions like, if we fix the number of particles, what might we expect to be the minimal energy, and what types of configurations might produce those? If that's particularly hard to find, what we might do instead is just look at asymptotics. What happens as the number of particles goes off to infinity? Do points nicely distribute and spread out along your space, or do they cluster and concentrate at certain points? And whether or not we can get these kind of informations about what the minimal energy we might expect to find is, we can also ask the question of how might we generate point sets that have, if not minimal energy, then sufficiently low energy. Can we do it by taking the expected energy of some random point set? Can we construct them deterministically? Could we sequentially put down the points one at a time and still find low energy? Or can we do some kind of gradient? Descent to find good numerical examples of point sets for minimizers? Things that I won't be talking about in this talk, but are also interesting topics in this, could be about dynamics, how when you place down particles, how they move under these kinds of potentials, what happens when you introduce non-zero temperature. So in this case, the case I'm looking at, everything is static, but if you made it be a non-zero temperature system, then particles are always moving, so they don't really have fixed points as much. And you can also ask about systems with external fields. So running through a couple of classical examples, the first one, the go-to is the Thomson problem, which dates back from over 100 years ago, which is exactly if you put electrons on some metal sphere, interacting according to Coulomb's law, what minimizes the electrostatic potential energy. And already something that would seemingly be very natural to look at, something that ideally should be a simple question, is actually already very difficult to answer. It's the result is only known for a scant few numbers of particles, and in fact the most recent one that was discovered a little bit over a decade ago actually took a computer assisted proof just to figure out what happens for 5 points. So actually finding explicit minimizers can turn out to be very, very difficult, and even numerically you can run into problems because the number of local minima can increase drastically as your number of particles do, and they may be far away from what the global minima are. But this is a classical example, though. More generally, we can look at Riesz kernels. So now for any set that's in Euclidean space, you just take the Euclidean distance, raise it to the power negative s, and then you're multiplying it by 1 over s, the idea being that it's always a decreasing function of distance. So if s is a negative number, you have a singularity when when s is a positive number, you have a singularity when the distance is 0, and then something that's decreasing towards 0. If s is a negative number, then you have a positive power of the distance times a negative number, so it's still decreasing. And then if s is 0, we take the logarithmic kernel instead. Some examples of where this has popped up. It connects to a wide range of other problems that involve nicely distributing points. So the logarithmic case, if your compact set is in R2, or you could say a subset of the complex plane, these minimizers are known as Fekete points, which are useful for interpolation. And there's a and right. So if on S2, there's a it was one of Stephen Smale's famous problems is determining an algorithm to produce point sets that that give very low logarithmic energy. So this is a open problem and one of the ones that Stephen Smale put forward. So if you wanted to pursue it and could get some nice results, that's a famous one to tackle. For S being -1, so this is the negative sum of Euclidean distances between points. This energy is actually equivalent to something known as the quadratic spherical cap discrepancy on the sphere. Discrepancy is basically a measurement of not just how uniformly distributed are you on the whole space, but on subsets of the space. And then it's also connected to a worst case error for numerical integration on a certain Sobolev space. These are results of Stolarski and Brauhart and Dick from respectively about 50 years ago and 10 years ago. So this is again connecting energy minimization to nicely distributing point sets, either with respect to discrepancy or numerical integration. A final neat result is that if you have some compact set and S is greater than its dimension, with some caveats, then the minimizing configurations are known to be well separated, so they satisfy some optimal bound of how far apart they must be from one another based upon the number of particles, and they're uniformly distributed, meaning that they approach the Lebesgue measure if you consider them as discrete probability measures. So this is something significant because here we have an example of the torus T2, but embedded in R3. And at S being 0.2, these red points here are your particles, and you'll notice that none of them are kind of on the inner part of the torus while everything's spread to the outside. And as we start increasing the repulsion, they start filling out the whole space, and then at S being 2 and then S being greater than 2, so the dimension of the space, they actually uniformly distribute on the whole torus. So it's not an insignificant thing to be able to get that things are well separated and uniformly distributed. But so the whole idea of this slide is that energy minimization we can connect to various ways of optimally distributing point sets, which has its nice uses. One other neat connection is that as the repulsion goes off to infinity, the energy minimization for these Riesz kernels actually becomes a best packing problem, which basically is a question of finding a configuration of endpoints on your sphere that maximizes the minimal distance between points. These are known as densest packings or optimal codes. And this problem is also known as the TAMS problem, and it's named after a Dutch botanist who was basically looking at the distribution of pores on pollen grains. But so over here you have an example of a packing. There's balls around each of the points, and basically the idea is that as S goes off to infinity, the repulsion gets so strong that you basically just have solid balls around each of your electrons. A different kind of energy that I would imagine some people here have some interest in is known as frame energy. So I'm sure many of you know this, but a set of points on the sphere is called a tight frame if and only if it acts as an overcomplete orthonormal basis, basically giving you an analog of Parseval's identity. Which is, of course, great for signal processing because basically by doing this, you build in redundancies. So if you have errors in your signal, you're more likely to be catching them with these redundancies. Now, these point sets are related to a certain energy, and this is a result of Benedetto and Ficus from about 2 decades ago, saying that a point set is a tight frame if and only if it is a minimizer of the frame energy with the kernel here, just the inner product squared. The really amazing thing about this result that's very uncommon is that it turns out that any local minimizer of this energy is also a global minimizer, meaning that it's actually gives a very nice, easy way to be able to find tight frames. Just need to find a local minima. Right, so some nice different connections to energy optimization and some reasons why we might want to pursue finding these kinds of point sets. Now, as I mentioned back near the beginning of the talk, for the Thompson problem, it can be difficult to actually find minimizers for any fixed number of points. So one of the problems we might pursue instead is what happens as the number of points goes off to infinity. To understand that, we want to look at what we call the continuous energy. So it's basically the same kind of object, except now we replace our summation with integration, and we are looking to minimize over probability measures. So instead of electrons, what you can now think of, we're trying to find a minimal charge distribution over some space. And we can ask the same types of questions. What measures minimize this energy? Is the equilibrium measure that you get unique? If you have some kind of nice space like a Riemannian metric, is this minimizer like the volume form? Is it some kind of uniform measure on the space? Does it have nice symmetries? If you can't find the measure, you could also ask, what can you say about the support? Is it full dimensional? Is it the full space? Is it lower dimensional? Is it discrete? And what geometric properties of the space and analytic properties of the kernel might influence these types of things about the dimensionality and whether or not support of the minimizer spreads out over the whole space or condenses and then is concentrated on some kind of small set. And some of a bit of this last point here is some of what the focus of the talk is here. But so this continuous energy, it connects back to the discrete energy because it turns out that minimizing the discrete energy in the limit ends up being the same as finding the minimal continuous energy. And in particular, if you have a sequence of minimizers of the discrete energy with a number of points going up and up and up, then the corresponding discrete measures defined here as probability measures converge in the weak star sense to minimizers of the continuous energy. So if we know what the minimizers are for the continuous energy, we should know what points are doing, what happens as the number of points goes off to infinity, how particles behave, where they concentrate to, or how they spread out. So in order to be able to get back to this discrete problem, we want to be able to say, okay, so for continuous energy, when can we expect this spreading out, or when can we expect minimizers to consolidate onto smaller sets? Once we have something like this result, so for instance, on the sphere, it's known that if we have the recent energy, so Euclidean distance raised to the power negative s, if we have this on the sphere, then the uniform measure on the sphere uniquely minimizes the energy if s is between -2 and the dimension of the sphere. These are classical results by Rees and Bjork from quite some time ago. But so this then tells us that, again, going from this last slide, this convergence we expect of discrete minimizers to the continuous minimizers, that the minimizers of the discrete Rees energies on the sphere need to be uniformly distributed, meaning that they're converging to the uniform measure in the weak star sense, if you think of them as probability measures. Using the script E sub k to mean the minimal discrete energy for endpoints, this result immediately tells us that for the Rees energies, the minimal energy for endpoints should have asymptotics like n squared times the minimal continuous energy plus something that's little o of n squared. And a result of Leopardi tells us that any sequence that's sufficiently separated and uniformly distributed will satisfy this first order asymptotic. And actually, in fact, it turns out that if s is between 0 and -2, well, we actually have a continuous kernel. So it's enough to just say that we have uniformly distributed point sets converging to the uniform measure, and this will give us the correct first order asymptotics. In the case where s is between 0 and d, we have a singularity, so we need this separation to be included to make sure that we don't have any 2 points that get too close to one another and spike the energy to infinity. So the problem with this is that this then tells us that if we want to look at energy to determine how nicely point sets are distributed, first order asymptotics don't necessarily tell us quite as much as we might want to know. So a way that we might measure uniformity of point sets, because again, energy is connecting to these other ways of measuring uniformity like discrepancy and packing problems, So a way that we might try to measure uniformity with energy is actually looking at second order asymptotics once we know the first order asymptotics. And so on the sphere, this has been very well determined by a number of results over the course of 2 decades. Basically, if you're on the sphere SD and S is between -2 and the dimension of the space, we know that the second order asymptotics of the minimal energy for endpoints is of order n to the 1 plus s over d. That should be a lowercase d, sorry. And so the way that you can look at a point set and determine how nicely it might be distributed is by seeing a sequence of point sets is you might look at how do their second order asymptotics behave? Do they stay in this range? Do they have this correct asymptotic order? If so, they're likely nicely distributed as they'd have very, very low energy. Right. And I should also say in the logarithmic case, instead it's slightly different. The second order term is an n log n instead of n to the 1 plus s over d. So the idea of using energy to determine nice point sets would be, when can we determine that the continuous energy is the uniform distribution, is minimized by the uniform distribution? Then we can go back to a discrete energy and say, okay, minimizers should be uniformly distributed. That tells us our first order asymptotics. It should look something like this, n squared times the energy you get from the uniform measure. And now we can look at second order asymptotics to determine how nicely point sets are distributed. So the question then becomes, when can we know that the uniform measure on space is a minimizer? Right. Before that, okay, I forgot that I had the slide here. Before that, we have, right, so the things to mention is that for s equals -1, that was the case where that was the case that the energy connected to discrepancy and worst case error for integration. And it turns out that these higher order asymptotics are exactly the asymptotics for minimal L2 discrepancy on the sphere. That's Stolarski's result. If you look at IID uniformly distributed random points on the sphere, that only gives you energy second order asymptotics of the power n. So not something quite ideal, which again suggests that you need to put in a bit more structure to have optimal point sets for the energy. And I will also say recent work that I had with a few collaborators showed that this result wasn't unique to the sphere. For any of the projective spaces, you could do something very similar. If you embed them into a sufficiently high dimensional Euclidean space, you can use the Euclidean, you can evaluate Riesz energy on them, and you get a very similar result. So this may be a more general phenomenon than just on the sphere. It may extend to a number of other spaces, and it's an interesting thing that I'm hoping to pursue. But right, so going back to the question, we want to determine when on certain spaces we know that the continuous energy will be minimized by some kind of uniform measure on the space. And a key property for this will be something called conditional positive definiteness. So we call a continuous kernel conditionally positive definite if for any configuration on the space, the corresponding matrix where the entries are given by the inputs, the points, that corresponding matrix is conditionally semi-positive definite. Which is defined over here. We want to be able to talk about minimizers for kernels that aren't continuous, that have some singularity when the distance is 0. So we need to extend this result, and we can do this by saying that a general kernel we'd call conditionally positive definite if for any finite sign Borel measure on our space with total mass 0, the corresponding energy integral is non-negative if it's well defined. And we say the kernel is strictly conditionally positive definite if the equality occurs if and only if that measure is equivalent to 0 everywhere. Now, what can I do with this? Well, you can actually get some pretty nice things. So the first thing, so we need some results out of potential theory. So the first is that if you have a measure that minimizes your energy, then the potential, which is this u sub k mu, which you get by integrating once with respect to mu, it has to be equal to the energy that you get everywhere on the support, or really almost everywhere on the support, but it's enough for the purposes of this talk to say everywhere on the support, and it has to be greater than or equal to that energy everywhere else on everywhere on the space. Now, what's really handy about this is that if you have a kernel that's conditionally positive definite and your mu satisfies the Dispersion conditions, then that mu is a minimizer of your energy. Moreover, if your K is conditionally strictly positive definite, then you know that that mu is the unique minimizer. So if we have conditional strict positive definiteness, it's enough to just check that a measure satisfies the Frostman conditions, and then we know we have the unique minimizer. Finally, another neat little result is that if you have a continuous kernel and you have a minimizer of your energy, then your kernel has to be conditionally positive definite on the support of mu. So there's these nice connections between measure being a minimizer and this conditional positive definiteness. Now, what do we get out of that? Well, if we restrict to certain spaces, we can actually say quite a bit. So suppose you have a compact Lie group G and a closed subgroup H, then their quotient is a homogeneous Riemannian manifold with a unique group invariant probability measure, which you would call the volume form for the Riemannian manifold, or the Haar measure, or you could say the uniform measure, which we'll denote by sigma. Since it's a Riemannian manifold, we had a geodesic metric, and for that metric, the Lie group G is the isometry group, and it acts transitively on our space, meaning that for any 2 points in the space, there's some group element that maps one point to the other, and this is what defines it as being homogeneous. There's plenty of spaces that are like this. Some nice examples would be any kind of rotation group, the tori, Grassmannians, projective spaces, spheres. So lots of different nice spaces. And what you now can get out of this is that if K is G invariant, meaning that if I take K of X, Y, and I apply a group element to both X and Y, it doesn't change the value of K. If we have that and that K is conditionally strictly positive definite, then this volume form, this uniform measure on the space, uniquely is the unique minimizer of the energy. And the proof of that's pretty straightforward. If you have a unique minimizer and some isometry in your group, then the energy with respect to mu could be written with the same kind of integral, but you apply G to both X and Y, but that's just the energy of the push forward of the measure mu with respect to G. Now, since the minimizer has to be unique, this means it has to be invariant under all group actions. And again, there's only one measure, there's only one probability measure on the space that's invariant under all the actions, and that's the uniform measure. So that's how we're able to get that. So, right, so if we can just figure out conditional strict positive definiteness, we get the uniform measure's unique minimizer. That means that minimizers of the discrete energy must be uniformly distributed, and we could start looking at what our second order asymptotics like to determine how nicely certain point sets are distributed. So the problem then that presents itself is that checking this condition for conditional strict positive definiteness is not necessarily an easy thing to do directly. How are you going to check the non-negativity of every single integral? Well, you do some harmonic analysis to work around it. So you can break down the space of square integrable functions with respect to the uniform measure on one of these homogeneous spaces into the eigenspaces of the Laplace-Beltrami operator, each of which having some orthonormal basis of real valued continuous functions, with the index zero space just being constant functions on the space. If you do that, then you can say that the following are equivalent for if K is a G invariant and continuous kernel on your space, then K being conditionally positive definite is equivalent to there being non-negative coefficients, B sub 1, B sub 2, and so on and so forth, such that K of X, Y can be written in a sum like this, where you're taking your different elements of the bases in X and Y, multiplying them, and then summing them up. And the coefficients are the same for all the elements of each of the eigenspaces. And this sum converges uniformly and absolutely. And then the final equivalent item is that the uniform measure minimizes the energy. If instead we replaced conditional positive definiteness with conditional strict positive definiteness, then these coefficients here end up being positive, and the uniform measure is a unique minimizer. For those of you that are fans of algebra, instead of the eigenspaces of the Laplace-Beltrami operator, we could instead break down our space of square integrable functions into irreducible representations of the isometry group, and the same thing is happening there. So then the challenge lies in the fact of whether or not we can know what these representations or eigenfunctions are, these phi sub kj's are, and determining these coefficients. If we can determine the coefficients and find them to be non-negative, then we can get the positive definiteness that we want, and then we can have that the uniform measure is a minimizer. So before I restrict myself to a bit of a smaller set of spaces, I will say some of these directions are relatively simple proofs. One of them is pretty nice and straightforward. So if in this expansion here, you know that you have if you know that you have non-negative coefficients and you have the uniform and absolute convergence, then for any probability measure, you can basically pull out the summations from integration, and then you have integration where x and y are entirely disjoint from each other. So now you just have a sum of squares of integrals, all of which would be non-negative, which means that this whole summation should be bounded from below by just the zero coefficient, which is exactly what occurs when you integrate with respect to the uniform measure. So this is how you get that the uniform measure would be a minimizer over probability measures. So again, the challenge is about knowing what these phi sub kj's are, and or figuring out what these coefficients are. But if we restrict to sufficiently nice spaces, then the computations for this can become very nice. So let's focus on the sphere. For the sphere, the eigenfunctions of the Laplace-Beltrami operator are just the spherical harmonics, and so we can separate onto spaces where for each space we get an orthonormal basis of spherical harmonics of degree n. Then for any 2 points on the sphere, if we take the sum of each spherical harmonic in x times the same in y, we end up getting that sum is actually some constant times a Gegenbauer polynomial of the inner product of x and y. And so Gegenbauer polynomials, they form an orthonormal basis to a space of square integrable functions on the interval from -1 to 1 with respect to a certain weight, which is exactly what pops out when you switch from integrating from spherical coordinates to cylindrical coordinates. And now what we can do with this is that if we have any function that's integrable with respect to this weight tau on this interval, then we can take the energy with respect to the uniform measure to basically be f of the inner product of x and y with respect to the uniform measure, and we can replace this with the integral from -1 to 1 of f of t with respect to that weight. And this would be the zeroth Gegenbauer coefficient, where f can be expressed in a sum of Gegenbauer polynomials in this kind of form, where each of the coefficients are calculated in exactly the way that you'd think that they would be. So this lets us switch from integrating over spheres to just integrating over intervals, so long as we know that we're dealing with kernels that only depend upon the distance between points, or since we're on the sphere, you can write that as the inner product between points. So one of the things that was lacking in this theorem over here, where some of the legwork had been done decades ago by Mercer, Bachner, Schoenberg, and Gangali, but consolidated into being related to energy minimization problems by recent work with Dmitry Bilik and Sasha Vlasyuk, we had to require that K is continuous, which, again, we want to be able to say what happens for kernels that have singularities when the distance is 0. So it'd be nice to be able to say a bit more. And when we restrict ourselves to the sphere specifically, recently in a paper with Joel Neff and Dmitry Bilik, we made some progress in extending those results out to singular kernels, and then Billick with Peter Grabner actually extended it to all functions that have a singularity at the origin but are continuous elsewhere. So if you have some function on the interval that is integrable and continuous everywhere, but when the distance is 0, so inner product 1, then the following are all equivalent. The uniform measure minimizes the energy over probability measures on the sphere. For all, that's equivalent to all of the Gegenbauer coefficients being non-negative, except for maybe the constant coefficient. And this is equivalent to the kernel corresponding to f of the inner product is conditionally positive definite on the sphere. So this allows us to use this property for things like Riesz kernels, which is pretty nice. Hello?
I think it's fine. Just unmuted.
Okay. Right. So we can say something a little bit stronger. So if k is conditionally strictly positive definite, then these equivalences all become strict. So the uniform measure is the unique minimizer, and the coefficients are all positive. There is an analog for projective spaces. It's just easier to write it for the sphere alone without having to introduce things for the projective spaces. And for general integrable functions, f, not just ones that are integral and continuous everywhere, but at 1. So far, the strongest result that's known is that if all the Gegenbauer coefficients are non-negative, then the uniform measure is the minimizer for absolutely continuous measures on the sphere. Hopefully, it's unknown whether or not that could be extended to all probability measures. Now, so from this, we're able to say, hey, we have this way of determining when the uniform measure is some kind of minimizer through conditional positive definiteness, which allows us to again determine point sets that might be really nicely distributed by looking at their second order energy asymptotics. Now, if f is continuous on the interval from -1 to 1, so a function of the inner product, but is not conditionally positive definite, we know that any kernel must be conditionally positive definite on the support of the minimizer of its energy. So if we have a minimizer, its support cannot be the full space if f is not conditionally positive definite. So the question is, okay, so if it's not the whole space, what might it be? And so from this point in the talk, things shift a little bit. So we've talked about what will guarantee us to have minimizers that are uniformly distributed on the space. Now we look at what happens if we start breaking the properties that give us that uniformity and seeing how that leads to minimizers being concentrated on smaller spaces. So in order to work up to that, first thing to introduce a little bit here are spherical designs. So we say a set of points on the sphere is a spherical M design if and only if it provides an exact quadrature formula for all polynomials of degree at most m on the sphere. And so what do we get out of that? Well, if f can be written as a finite sum of Gegenbauer polynomials with non-negative coefficients, in other words, it's conditionally positive definite polynomial on the sphere, and we have some m design, then the energy of the probability measure corresponding to the design, where we equally distribute mass along all the points of the spherical design, is the same as the energy we get from the uniform measure, which we know is the minimal energy for conditionally positive definite kernels. So that's something that lets us know that we can have discrete minimizers in this kind of case. And results by Botarenko, Rodchenko, and Vyazovska show that for in any dimension, once the number of points gets sufficiently large, there always exists spherical M designs of that number of points. So as long as we have conditionally positive definite polynomials, we know not only can we get the uniform measure as a minimizer, but we can get discrete minimizers as well. And this result can be extended somewhat, and this is what we did with work with Billick, Glazier, Park, and Vlasyuk a few years back. So suppose you have some function f for which the Gegenbauer expansion has the following property, that finitely many of its Gegenbauer coefficients are positive. You might have infinitely many being negative or not, but only finitely many are positive here. Then there always exists a discrete minimizer of the continuous energy, and you can get a bound on the support of the minimizer, which is basically a sum of the dimensions of the eigenspaces of the Laplace-Beltrami operator that correspond to the coefficients that you get that are positive there. So these are the spaces of spherical harmonics of degree n on the sphere SD. So yeah, that's so if we in a certain sense break positive definiteness by making sure that we only have finitely many positive coefficients, then we can know that there exist discrete minimizers as opposed to anything being uniform. Right. So this tells us existence. It would also be nice to be able to say, when do we know that we only get discrete minimizers? And so that right. Before that, so the collection of the result here, and from what's before, is that we can say that if you have any polynomial kernel f, there always exists a discrete minimizer, because you would never have infinitely many positive coefficients if it's just a polynomial. And if a polynomial f is not conditionally positive definite, meaning that it has some negative coefficients, then we were also able to prove something a little bit stronger than just this result here. We were able to show that the support of any minimizer has to have empty interior on the sphere. So in this case, we know there exists a discrete minimizer, and we know that there can't be a minimizer that has any interior on its support. So we'd now like to be able to say something about when do we know that we only get discrete minimizers. And for that, we're going to shift over to talking a little bit about p-frame energy. So near the beginning of the talk, I mentioned frame energy, where you took the inner product square, and here we're replacing inner product with t. For the p-frame energy, which was, I believe, introduced by Aileron and Okujo back in 2012, we basically take the absolute value of the inner product between x and y and raise it to the pth power. And then we're interested in what are the minimizers of the corresponding energy on the sphere. Now, if p is not an even integer, it turns out that the Gegenbauer expansion of this kernel has infinitely many positive Gegenbauer coefficients and infinitely many negative Gegenbauer coefficients, which means that we can't use this result here because it fails to satisfy this condition, which makes it an interesting, which made it an interesting test case to look at. Other reasons why it was interesting to look at, it turned out it had some neat connections. So for certain values of p on certain spheres, it turned out that if you minimize its energy, if they existed, equiangular tight frames would minimize this energy. Which I believe the signal processing community really likes equiangular type frames. In convex geometry, there was a neat connection between minimizers of this energy and LP mixed volumes. And in quantum mechanics, minimizers had a connection to symmetric, informationally complete positive operator value measures, which are known as sigpovms, also connected to equiangular type frames. So there were some neat connections that kind of drew us into this. You'll notice that if p is equal to 2, this is just the frame energy. So Benedetto and Ficus's results tell us that tight frames are minimizers. We also were able to say that the uniform measure is a minimizer. In fact, any measure that's isotropic would be a minimizer. If p is greater than 2 but is an even integer, then the uniform measure is a minimizer, because you just get a positive definite polynomial of the inner product here. And because of that, yeah, so you get the uniform measure as a minimizer, but you also get that spherical designs are minimizers. And this was something that was studied by Sadelnikov back in '74. Now, what started being a bit unusual to see occur was what happens for all other values of p. So in 2012, Aileron and Okujo started studying this object and found that if p was between 0 and 2, a uniform distribution on an orthonormal basis was a minimizer, but no other frames were minimizers of this energy, nor was the uniform measure on the sphere a minimizer, which you shouldn't expect because you have negative Gegenbauer coefficients. Right. So currently the conjecture is that if P is a non-negative integer, then all minimizers of this energy should be discrete. And there's some reasoning to that. So in order to build up to that, though, I need to talk a little bit about how one can do linear programming bounds for energy. So suppose you have some kernel f, function of the inner product, and some other function g both of which are continuous, such that g is a conditionally positive definite polynomial of degree at most m. That g bounds f from below on the whole interval. And then suppose you also have some spherical M design such that for all points in the design, the f at the inner product of those 2 points is the same as g at the inner product of those 2 points. So this would be an example here of an f and g bounding from below, and then these points where they meet are where you have the inner products of the design. Then for any probability measure on the sphere, the corresponding energy for f is bounded from below by the corresponding energy for g, because g is less than or equal to f, so it must have a lower energy. Since g is conditionally positive definite, we know the uniform measure minimizes that energy. Since it's a polynomial of degree at most m, we know we get the same energy for our spherical M design. And because at all of the corresponding inner products, g is the same as f, that means that that's the energy that f has for the measure that corresponds to the spherical design. So this tells us that if we can do this kind of construction, then the energy we get from these spherical designs give us a lower bound, give us a minimizer of the energy for our function f. So designs can yield minimizers. To construct a g that does exactly what we need here, we can make use of Hermite interpolation to construct that kind of polynomial, where we interpolate once at the endpoints, and we interpolate twice at every point in between the endpoints. Because of that, though, that actually means that g can have quite high degrees, so we need designs that have very few distances to kind of keep the degree of g down. So the types of designs that we need are tight designs. So a spherical tight design is basically a design of some given strength that has the fewest number of distances between its points possible for that strength. So in the case where you have a 2m+1 design, this means that it's centrally symmetric and there are exactly m+2 inner products between points. If it's a 2m design, then it just means that there are m+1 inner products between its points. So these only occur with incredibly symmetric configurations. They're very rare. They tend not to exist, and they're very hard to find. But when they do exist, again, they're very nicely structured. So some examples would be the vertices of a regular simplex or a cross polytope on the circle S1, the vertices of a kagon on S2, and the vertices of an icosahedron, the elements of the E8 lattice or the Leech lattice, or points that you get from equiangular lines passing through the sphere. These are some of the constructions that give you tight designs. This what I'm showing here is not a complete list of them, but it covers most of the known tight designs on the sphere, on the spheres. So they're relatively rare, but they have very few inner products, which is what we need to keep the degree down so that we can have the design actually work on the polynomial. So, we can now apply this to sort of break a different thing that leads to positive definiteness. So again, in each of these instances, we're basically breaking some kind of property that leads to positive definiteness to get discrete minimizers. So we call a smooth function f absolutely monotone on the interval from -1 to 1 if all of its derivatives are non-negative. And then something that's known in classical and potential theory is that if the derivative of this f is absolutely monotone on the interval from -1 to 1, then the corresponding kernel for f is conditionally positive definite, so the uniform measure minimizes the energy. So now let's break that. Suppose that you have some continuous function for which the first m-1 derivatives are all non-negative on the interval from -1 to 1, but the this should be n less than or equal to m. But the m plus first derivative is non-positive on the interval from -1 to 1. Then for any tight m design, the corresponding measure is a minimizer of the energy, overall probability measures. Moreover, if you know that this m plus first derivative is negative everywhere, then tight m designs provide the only minimizers of the energy. So meaning that you only get discrete minimizers in that case. This doesn't just work for the sphere. There is an analog that works for tight projective designs on the real complex quaternion and octonion projective spaces that works just as nicely. And in fact, we needed to be able to do this on the real projective space in order to be able to have some statement for the p-frame energies. But this leads us to this result here. So if you have a tight 2m plus 1 design on the sphere, and p is between 2m minus 2 and 2m, then the corresponding measure to your tight 2m plus 1 design is a unique minimizer of the p-frame energy. So you only have discrete minimizers for breaking this absolute monotonicity that leads to, which in that case would lead to uniform distribution. Breaking it correctly seems to lead to discreteness for minimizers. Now, this also works for p between 8 and 10 on S3 if you take the 600 cell, which is not a tight design, but the theory ends up still working out quite nicely. The minimizations. So what this tells us then is in these kind of cases, energy minimization results in tight designs if tight designs exist, which suggests that this could potentially be a way of finding tight designs if they're not known, is by trying to find minimizers for these energies, and they might produce something like that. Outside of that, this also suggests that weighted designs with very few distances between the points or having very low cardinality for their strength might provide minimizers for these kinds of energies more generally. And in fact, when we were numerically looking at minimizing these p-frame energies, we actually came across a few new weighted designs that seem not to have been discovered before. Not tight ones, but ones with very few inner products compared to their strength. Numerically, we found for all p-frame energies that we could test that it always seemed like minimizers were discrete if p was an even integer, and this is what we conjecture. It would be interesting to find out whether or not that's true. So far, the progress that we've made towards that, aside from determining certain instances when there are discrete minimizers, is being able to say that if p is not an even integer and you have a minimizer, then then the support of that minimizer must have empty interior. Hopefully in the future, more progress can be made for that. And I think with that, I will stop my talk there. So thank you all very much for your attention. Hope that you found that interesting.
Thanks, Ryan. I'm going to thank our speaker by clicking buttons, specifically the clapping hands button.
Thank you.